So have a look at the content. Okay, single layer perceptron. So these are the important topics in that single layer perceptron. So we have to define a single layer perceptron. So the concept of perceptron was given by Rosenblatt during 1957. Perceptron indicates the simplest form of a neural network. So the simplest form, that is nothing but a, we are representing a neural network with a single neuron, that is called as a perceptron. Okay, which is used for the pattern classification. So here uh, that single neuron that you are considering in this neural network, that is helpful to make the pattern classification. I think in the previous class we discussed what is meant by pattern classification, how we are making a classification of a pattern. Okay, so perceptron is a neural network so in perceptron what we are doing, perceptron is nothing but a simplest. If we are going to represent a neural network with a simple single neuron, that is called as a simply perceptron. Okay, so here that kind of single neuron which is helpful for the creation of a neural network, we can use such kind of perceptron for classification. Okay, for classification of patterns. So what is a pattern? When we give certain inputs, we are expecting to get a kind of output. That means for the input pattern, we are going to get an output pattern. For one kind of input, when we give, we are getting one kind of output. For another kind of input that we are giving, we are getting another kind of output. So for there are two kinds of patterns here. For one kind of input that we are giving, suppose we are giving all even inputs. For that, we are expecting to get a output of one form. We are giving all odd outputs. For that, we are expecting to get another kind of output. So there is a pattern there. Okay, for even inputs, there is one kind of output pattern that you are getting. For odd inputs, you are having another kind of output pattern. Okay, so that is called as a pattern. So here there are two kinds of perceptron. So single layer and multi-layer. With respect to unit 2, we are being discussing with respect to single layer. In unit 4, we can go with a multi-layer. So the last topic is nothing but the limitations of a perceptron. Okay, so what are, that is the limitation of a single layer perceptron. To overcome that one, we are going with a multi-layer perceptron in the next unit. So single layer perceptron means definitely you are going to have a single neuron with respect to which you can frame the neural network. So here the output of a neuron may be either +1 or -1. +1 means it belongs to one category, -1 means it belongs to another category. So this is a Rosenblatt's simple representation of a perceptron. If we consider, okay, the representation, there is a sensory units from where we are considering the required inputs. Okay, we are not considering all the inputs. We are giving only selected inputs. Okay, we are giving or we are taking only selected inputs. Those selected inputs are given as the input. Every input is associated with certain weight function w1, w2, okay, so on up to wm, as we are considering with respect to m number of inputs. So all these are being forwarded to an activation function. That activation function is nothing but represented by phi of nu. Okay, so after that that phi of nu, we are going to apply a step function. Okay, so that is nothing but an activator with the help of which we are going to get the output here. Okay, so these are the things which are being associated. So we are having the activation function, output signal, error. What is that error? Every time for any kind of neural network, for a given input, we are expecting one kind of output. If the obtained output is different from that of the actual output, definitely there is an error. Error is nothing but a desired output minus or actual minus desired one. Okay. So this is a pattern. So this is a pattern classifier. So this is one kind of pattern, one class of outputs that we are getting. This is another class of output that we are getting. If successfully we are going to separate these two, we can call that plane, that line or that hyperplane as a classifier. Okay. In 2D, that classifier is a line. In 3D, that classifier is a plane. In more than 3D, that classifier is a hyperplane. Okay. So if such kind of classification is going to be carried out successfully, that is called as the two patterns to be, we can term them as linearly separable. Okay, next. So structure of a learning perceptron. So generally, if we have a look here, so look at the structure of a perceptron here. We are considering single neuron. Okay, single neuron. For this single neuron, we are giving m number of inputs. Okay, x1, x2, so on up to x suffix m. Okay, x suffix m inputs. All the inputs are associated with the weight functions w1, w2, w3. Next, if we observe all these, the combination of the input along with the weight function are combined together at one point. That is nothing but the uh, local field that is generated, which is represented by nu. So nu is the summation of the inputs along with the weights plus the bias that we are giving. Okay, so thereby which we are getting a activation function phi of v and an output y. So this is called as a that equation. Okay, this equation of this particular local field that is generated by the combination of this input and output, this input weight function along with the weight input values along with the weight. Okay, so at the uh, see at the local field, what we are doing, how we are getting that local field nu or small v, whatever it may be, that nu is nothing but a summation of the product of input that we are giving to the neuron. Each input is having certain weight function. Okay, the product of these two along with the bias. Okay, so that is considered. So we are going to, whenever we are connecting that one to the bias, we have to go with a hard limiter. Hard limiter means what? We are not considering all the outputs here. We are considering only the required outputs. For that, that's why we are imposing certain sort of limit, hard limit. Okay, so here for as we said now, that this single layer neuron or perceptron is going to act as a classifier. So what kind of classifier? Suppose if we are considering a set of input x1, x2, x3, so on up to x suffix m. So the output of these two, the output of all these inputs are going to be carried out in two kinds of output classes, that is C1, C2. Okay, if C1 is represented as +1 output and C2 is considered as -1, that means what? If we are going on giving, suppose I gave x1 as the input, I have considered that input. At that time I may be getting output +1. So I am considering that x1 belong to the class C1. Next, I have chosen input x2. At that time, I got a output -1. So I have chosen x2 to belong to a class 2. Okay. When I go on repeating like this, so all the inputs that I am giving, they come and fall under two categories. What are they? Either class 1 or class 2. Okay. Class 1 means +1, class 2 means -1. So whatever it may be either 0 or 1. So +1, -1, whatever it may be. So for all the inputs, when we give to a single neuron, we are getting the output to be classified into two classes. Those are nothing but class 1, class 2. Okay, so here these class 1 and class 2, as we said, they are going to be separated by a classifier. Okay, that classifier is represented by this equation. Okay, that is equal to 0. This equation that represents the classifier between two classes, class C1 and C2. So this particular boundary, okay, that particular boundary, suppose if I am considering only two inputs x1, x2, then what is the equation of that boundary? As every input is considered as every input is associated with a weight function x1, associated with a weight function w1, x2 associated with a weight function w2. So how can I write this equation if I am going to consider only two inputs? So that is nothing but w1 x1 plus w2 x2 plus b equal to 0. So that is the boundary. This is the boundary. Okay, so sometimes what happens when we consider class C1, so this condition may be greater than 0. If for class C2 it may be less than 0. So for all the remaining things for which this equation becomes 0. That is considered as the boundary between the two classes. So as the two classes are successfully separable with respect to that boundary, we can call that one as those two classes are as linearly separable. So for that one, consider two examples. So what are they? So consider an AND gate. So consider two inputs of an AND gate. AND gate represents a ordinary multiplication. When the input is 0 0, just have a look here. When the input is 0 0, we are getting an output 0. I have represented that output with a dark circle. These are the inputs 0 0. Next 0 1. 0 1 means on x-axis. Okay, that is on x-axis the value is 0. Okay. Next 0 1. 0 1 means I1 I2. So I1 is, see, I1 0, I2 is 1 1. Okay, 0 1. Next, for 0 1, what is the output? 0. And we have represented that one with a dark circle. Again for 1 0, 1 means I1. I1 value 1. That means this is 0 0. I1 means here. So when I1 is 1, I2 is 0. Okay, 0. So what is the result? 0. Again I have represented that one with a dark circle. When I1 is 1, I2 is 1, the output is 1. So look at this classification. So for one category of input, as I said now, so this was the input, 0 0 was the input, 0 1 was the input, 1 0 was the input, 1 1 was the input. So for each category of the input, the output is going to fall between two classes. What are the classes here? Class 0, class 1. Okay, if you have a look at the output, we are getting only two kinds of outputs, either 0 or 1. Okay, that is class 0 and class 1. So class 0 indicates what? Those are represented with dark circles. Class 1 represented with a, see, just have a look here. That is nothing but a hollow circle. So there exists a boundary that is successfully making a separation between the two classes. So then we can say that the two classes are linearly separable. Okay. So here C1 and C2, class 0 and class 1 are linearly separable for AND gate. Now consider an OR gate that represents an ordinary addition. So same here also, 0 0, input is 0, represent output is 0, represented with a dark circle. Next 0 1, the output is 0 0 1. So I1 0 1, output is 1 with a hollow circle. 1 1, output is 1 with a hollow circle. 1 0, output is 1 with a hollow circle. So here also there are two classes, class 0, class 1, and both are separated with a linear, both are being linearly separable with the help of a small classifier. Next, consider one more special case. What is that one? Exclusive OR. In exclusive OR, so when the output is equal to 1 or when the output is equal to 0, in exclusive OR the output is 0 when all the inputs are same. In exclusive OR the output is 1 when any one of the input is different. So 0 0 output is 0 because both the inputs are same. 1 1 output is 0 because both the inputs are same. 0 1 output is 1 because one of the input is 0. 1 0 the output is 1 because one of the both the inputs are different. See there, for this kind of classification, for this kind, here also what happens, there are two classifiers, class 0, class 1. But in this kind of classifier, if you observe here also we are getting, okay, both classes, class 0, class 1. But this is class 0, these are class 1. But try to draw a line such that it is going to separate these two boundaries. Is it possible for us? No. Okay, so that's the drawback of the singular perceptron. It doesn't work well with respect to the exclusive OR. So for the next chapters that you are going to learn, whether that is radial basis function, whether that is a multi-layer perceptron, you have to go with the application of all these. What are the AND gate, OR gate, exclusive OR? There also by using the present scenarios, that means how we can utilize these things. By using the present scenario, you can calculate them. Okay, calculation means what? In singular perceptron, exclusive OR is not successful, not linearly separable. So we have to achieve that approach. How we can carry out that approach? By using a multi-layer perceptron. So the next one is nothing but a adaptive filtering problem. So have a look at the diagrams once. here we have to consider a system. Okay, so what is the working of that system? Some sort of inputs are given. We don't know the nature of the system. Okay, so that's a dynamical system. Some sort of input is given. We are getting a kind of output for the given input. We are getting a kind of output for the given input. So this is a signal flow diagram for the diagrammatical representation here. So here we are going to have, see, we are having a system whose nature is not known to us. For this system, some sort of inputs are given. Okay, for these given inputs, we are getting a kind of output, desired output di for the inputs x bar of I. So the external behavior of the system, we are getting the output. Output is nothing but we are getting the output. So there is a set t. There is a combination of input and output. What is that input? X bar of I. What is that output for that x bar of I? That is d of I. What is that x bar of I? That is nothing but a vector, consists of numerous inputs, x1, okay, x2, x3, so on, x suffix m. So here we are going to have two kinds of inputs. One is spatial, another one is temporal. For whatever may be the spatial or temporal, we are going to get a output. So if we have a look here, the output yi is produced. See, when we are giving an input x of I, we are getting an output di. So here what happens? Di is the desired result. Yi is the desired out. Di is the desired result. Yi is the actual output. But we are not getting yi. We are getting di. So definitely there is a occurrence of error. Why? Because actually we have to get yi, but we are getting di. So if di is not equal to yi, definitely there is an error. What is that error? Ei is equal to di minus yi. So this is a diagrammatical representation. So here we are getting the output as minus. Okay, see, minus means what? That's what we are getting the output as yi minus di. Okay, so this is the signal flow diagram. So yi is equal to the output yi, that is equal to nu I. This one. Again, what is nu I? Summation of, product of, okay, input into weight function. Okay, so yi is nothing but how can we give yi? So x transpose of input into weight function, where w bar of I is nothing but w1i, w2i, w3i whole transpose. Okay, so this is the adaptive filtering problem. So there is a system which is a dynamical system. We don't know what we are getting from that dynamical system, but for every kind of input xi we are getting an output di. Okay, so here we are giving xi by considering two things. What are they? That xi may be a spatial input or that may be a temporal input. Spatial input means what? You are selecting the input from the given set. Temporal means what? Temporal means you are selecting the inputs. What is the nature of these inputs? These inputs are linearly separable from each other. These inputs are separated from equal distances from each other. Okay. Next, for every input that you are getting, you are expecting to get a output di. So here actually di is the desired output, yi is the actually output. So definitely there is a difference between actual and desired. So that's why there is a occurrence of error, that E is nothing but di minus yi. So what is yi? Yi is nothing but equal to nu I. Again, what is nu I? Nu I is nothing but a summation of the product of input and weight function. Okay. So here we can write the same as x transpose w bar of I. So this is the error. So that was spatial thing. Next, unconstrained optimization techniques. Unconstrained. Unconstrained means what? Constrained means you are imposing certain sort of implementation, certain sort of conditions, and then you are getting optimal values. That's well and good. In the previous unit two also you have observed that constrained optimization techniques. Here you are learning the concept of unconstrained optimization technique. Unconstrained means what? You are not imposing any standard conditions, any standard boundary conditions there. So for that also you are expecting to get certain optimization or optimal outputs. For that you are going to follow unconstrained optimization techniques. So optimal means what? Exact. Okay, somewhat that is profitable. Optimal means that is a optimal cost, or that is nothing but best example for that one is nothing but traveling salesman problem. I think you are well familiar with that one, traveling salesman problem. That is nothing but we have to find a particular path that gives a profit. At the same time, what are the conditions there? The condition is nothing but we have to visit all the cities. Each city should be visited only once. There should be no closed path, or no other city should be repeated number of times. So such kind of things are nothing but constraint. That means conditions are there, conditional techniques are there. But here we are studying the concept of unconstrained. That means without any boundary conditions. So for that one, we are saying the concept of optimization. That means some critical value, some profitable value. Okay, some profitable thing that we have to get it here. For that purpose, we are considering a cost function C of W bar. So that cost function should be, we have to get an optimal value. So optimal value means what? Exact, a profitable value you have to get. When you can get an exact value or exact profit, when the considered value, the considered parameter should be an optimal parameter. That means we are considering a cost function C of W bar, that is a continuously differentiable function. Okay, that is nothing but W bar means that's a weight function. Okay, so what is the optimal condition here? C of W bar should be less than or equal to C of W. What is C of W? That is a cost function with respect to certain weight, that should be less than the cost function of the optimal weight. Why we are calling that one as optimal? Because we are not considering all the weight functions. We are considering only that particular weight function for which we are getting a profit. In diagram of a perceptron, if you see here with respect to every input, every input is associated with a weight. But we should not consider all the weights. We have to consider only that particular weight that is useful for us. That is called as optimal weight. So to get a optimal weight, this is the condition. Okay. So this is the thing that need to be satisfied. At the same time, there is a condition, that is the derivative, okay, of the gradient of the optimal weight should be equal to 0. So that is the gradient, okay, nebula. Next, gradient nebula into C W star. What is C W star? That is called as the optimal weight. Okay, cost value of the cost function of the optimal weight. So the gradient of this cost function considered at an optimal weight should be equal to 0. Then only we can say that we are getting the optimal condition there. So the gradient is nothing but given as dou by dou W1, dou by dou W2, so on. If you are considering m inputs, that is dou W suffix m whole transpose. So apply the same here. Okay, then we get a equation. What is that? We are getting these things there. So the starting weight is nothing but W0 initial weight, that is followed by the remaining weights W1, W2, so on. We are considering the cost. How to solve these unconstrained optimizations things by using three methods. What are they? Method of steepest descent, Newton method, Gauss-Newton method. So method of steepest descent means nothing but it is somewhat similar to that of two cases we have to consider. Steepest descent. Steepest descent is nothing but it is similar to the thing that somewhat when you are coming down a hill. When you are coming down a hill, there are two conditions. What are they? If you step down slowly, if you are going to come down to the hill fastly, then what happens? Two conditions are going to arise. If you are slowly stepping down the hill, it takes a bit of time for you to reach to the ground level. Next, what is another thing that you observe when you come fastly down the hill? Are you able to stop at the ground value, at the ground of the particular hill? No, definitely. You are moving in such a fast that by coming down also you are unable to stop. Again, you move to the uh, upside of another hill that is beside the first hill. Okay, so that sort of method is nothing but called as method of steepest descent. So just have a look here how this method of steepest descent is going to work. The successive adjustments applied to weight are in the direction of the steepest descent. That means if you are going to apply the condition along the direction of the weight. So here the direction of the weight is in one direction and the gradient that we are considering is in the opposite direction. Okay, so that's why gradient G is nothing but given as nebula over cost function C of W bar. On applying that, we are going to get a condition. What is that condition? W bar of n plus 1 is equal to W bar of n minus eta G of n minus eta G of n. That is already we know how we can calculate the change in weight function. Change in weight delta Wn, change in weight. Okay, how the change in weight is carried out? Change in weight is nothing but new weight minus old weight. What is the new weight? W bar of n plus 1. What is the old weight? W bar of n. That is equal to how much? Minus eta G of n. What is eta? Learning rate parameter. Okay, eta is nothing but the learning rate parameter. So W bar of n plus 1 is equal to W bar of n minus eta G of n. How we are getting this equation? Because here we are considering a expansion of a Taylor series. Taylor series expansion of this gradient of cost function. Then we got an equation like this. But already we know that the change in weight is given as W bar of n plus 1 minus W bar of n. New weight W bar of n plus 1 minus old weight W bar of n. That is equal to minus eta G bar of n. Okay. Next, as I said, there are two conditions in steepest descent. Either we can move slowly or we can move very fast. When we are moving very slowly, what happens? We can reach the steepest descent. We can reach the ground value slowly. Okay, so there is a curve like this. So these are for different values. For n equal to 1, n equal to 2, n equal to 3. That means for first input, second input, third input, like that. So this is for smaller, that means when you are moving down slowly for eta equal to small. Eta is what? Learning rate parameter. Now consider another thing. When eta is large, eta is 1, at that point what happens? You are coming down the hill very fast. So when you are coming down the hill very fast, you are unable to stop at the ground level. So this zigzag path, if you observe that clearly, there is a zigzag path. That zigzag path, see, there is a sawtooth like path that you are getting when you are moving coming down very fast. So that is for eta equal to large. So n equal to 0, n equal to 1, that means for the first iteration, for the first input, for the second input, like that. Okay, so that was a method of steepest descent. So here we have considered the same gradient cost function. Here what is the condition that we are seeing as we are moving down? The always the gradient, the cost function that we have considered is opposite to that of the gradient. So that's why we are considering the gradient function. Gradient is equal to nebula C bar of C of W bar. Okay, nebula C of W bar. Okay, that is G is equal to nebula C of W bar. These are the two things. Okay, first method is the steepest descent that we have completed. Next is the Newton method. So in Newton method, what happens? Again, we are considering the same cost function, and we are going to expand that cost function in Taylor series, and we are considering the first order value of a Taylor series. So this is a gradient of C of W bar of n, the same that we have considered now. For that one, we are applying, okay, we are applying second order Taylor series. When we apply first order Taylor series, we are getting this equation W bar of n plus 1 is equal to W bar of n minus eta g of n. Now we are applying second order derivation. Why we are going with a second order Taylor series? Why not a first order Taylor series? Because in first order Taylor series, if we move, we are getting two sort of that is conditions. What are they? When eta is small, we are getting under damped. Okay, when eta is large, we are getting over damped. So these are the two conditions that we are facing here when we have considered the first order Taylor series expansion of that gradient cost function. Okay, so now we are considering second order Taylor series expansion of this gradient of the cost function. When we consider the second order derivation of the Taylor series of this gradient cost function, that is given as C of W bar of n plus 1 minus C of W bar of n. Okay, on expanding this one, on expanding this, it can be written as gradient transpose of n, okay, delta W bar of n plus half, okay, so W transpose n. So here we are getting one matrix H of n. That H of n is nothing but called as, this matrix is called as a Hessian matrix. So what is the value of that matrix? So that is nothing but a nebula square C bar of W bar, C of W bar. That is dou square C by dou W1 bar, dou square C by dou W1, dou W2, so on. So here we are getting one. What was the drawback of the steepent descent method? We are getting values, well and good, but there are two drawbacks. Either we are getting very low value or either we are getting a high value, but we are not getting a fast value. To get that fast value, we are considered second order Taylor series expansion of the cost function. On expanding the second order Taylor series, we are getting this equation. So where capital H represent the Hessian matrix. Next. Okay, well and good. We have considered the second order Taylor series, but we are talking about the optimal values, na, minimized values, na. How we can get the minimized values? So for the obtained value, we have to perform the minimization. So that minimization is carried out by, though we are going to differentiate the obtained second order Taylor series expansion with respect to delta W bar. So now perform the same thing. So here if we perform the derivation of the first term with respect to delta W, see there, if we perform the same thing here, what happens? This delta W bar n, this delta W bar n gets cancelled. So what is the first term left? We are left with G of n plus, look at the second term. Here also we are having delta W bar of n. Here also we are having delta W bar of n. So both the things are going to be cancelled. We are left with this one. So from here, that is equal to 0. So we are left with G bar of n plus H of n delta W bar of n equal to 0. We want the change in weight. Okay, that is nothing but delta W of n is equal to this one. Already we know what is that one. How to represent change in weight? Delta W is equal to delta W bar of n plus 1 minus W bar of n. Change in weight. How? What is the value of that change in weight? New weight minus old weight. What is the new weight? W bar of n plus 1. What is the old weight? W bar of n. But actually we got an expression with respect to delta W bar of n. Substitute it here. Okay. On solving, we are getting this expression. Okay. Substitute it there. We are getting W bar of n plus 1 is equal to W bar of n minus Hessian matrix inverse of G of n. But the same when we considered here, we got delta W bar of n is equal to W, or this is W bar of n plus 1 is equal to W bar of n minus eta G of n. So these are the two things. Here we have to get a optimal value. For getting the optimal value, we are considering three unconstrained methods. Okay, of which the first one is method of steepest descent. Next one is Newton method. Third one is the Gauss-Newton method. Method of steepest descent. When we talk about the method of steepest descent, two drawbacks. Either we are getting low value, either we are getting higher value. Underdamped, overdamped. Overdamped, underdamped. To overcome that, we are going with the Newton method. Here, we are not considering the single order, first order Taylor series expansion of the cost function, due to which we got a drawback in steepest descent. So that's why we are moving with a second order derivation of the steepest descent, that cost function. Okay, so after solving that one, we are getting a expression for the new weight. W bar of n plus 1 is equal to W bar of n minus Hessian matrix n into G bar of n. So here also, what is the value? W bar of n plus 1 is equal to W bar of n minus eta G of n. So this is the change in weight, new weight value that we have to add. Why we are adding these things? Because when we consider output, we are not getting the same output as the one that we are desiring. We are not getting y of I, we are getting some d of I. Okay, so that's why the d of I is not equal to y of I. That's why we are getting an error. To overcome that error, what we have to do? We cannot change the weight value. We cannot change the input values. What is the only option that is left to us? We can change only the weight values. Now, how to change the weight values? By using method of steepest descent. This is the value. Okay. Next, by using Newton method, how to change the new weight? This is the value. What was the drawback of steepest descent? Either overdamped or underdamped. What is the drawback of this Newton method? The process is a bit, that means we are getting the output takes a bit time to be obtained, but it is a very quick process. Okay, so now to overcome the drawback of this Newton method, we are discussing Gauss-Newton method. In Gauss-Newton method, what happens? We are considering new value of the cost. Up to now we have considered the cost function C of W bar. Okay, C of W bar. Now we are considering a new cost function. So what is that new cost function? That C of W bar is equal to half sigma I is equal to 1 to n E square of I. E square of I. When we are considering a new cost function, definitely there will be a new error. What is that error? E prime of I comma W bar. E prime. Okay, E prime. That is a new error. How to represent that new error? That new error is nothing but E of I dou by dou W bar into E of I whole transpose. Okay, so when we expand this one, here also we are considering second order Taylor series expansion of this new error. Then we get E of n plus j bar of n into W bar minus W bar of n. So this is the new weight value, new error. But actually what we have to calculate? New weight W bar of n plus 1, not E prime of n of W. So that's why here again we got one more matrix J bar of n. That J bar of n is nothing but called as a Jacobian matrix. In the previous Newton method we got a Hessian matrix. Similarly here we got a Jacobian matrix. So this Jacobian matrix is different. So this is nothing but only here we are having only first order. Dou by dou W1. Okay, dou by dou W2. Dou so on, dou by dou W M. So like that. Next, every time what we are doing, we are minimizing we are trying to get the optimal weight values. So this is of the form, just have a look here. We are going to expand this term. This is of the form C of A plus B is equal to C is equal to A plus B. C transpose is equal to A plus B whole transpose. Next, C into C transpose. What we are getting? A plus B into what is C? A plus B. What is C transpose? A plus B transpose. On multiplying them, what do we get? A into A transpose plus A into B transpose plus B into A transpose, B into B transpose. So A into A transpose, B into B transpose, that is nothing but modulo of A square and modulo of B square, that becomes. So this is somewhat similar. See there. Let this be C. This is A and this is B. Okay. Now you have to consider C into C transpose. So make the simple multiplication of that one. Are getting what I am saying? So error here, that is equal to A E C. Let this be C equal to A plus B. Now multiply that one. C is equal to A plus B. C transpose is equal to A plus B whole transpose. So the same we are doing here. We are making a multiplication. So when we multiply A into A transpose, it becomes modulo A square. That is half modulo E prime n comma W bar square. That is equal to. Okay, just solve this one. You will get it. Previous class I said about a detailed solution of this one. We have discussed that one. So at last the new weight value that we are getting is W bar of n plus 1 is equal to W bar of n minus J transpose of n, J bar of n plus delta inverse. This entire delta inverse I can replace that one with another value, J bar of n into E of n. So we have moved with a steepest descent. Steepest descent, two types of drawbacks. What are they? Over damped, under damped. To overcome that, we are moving with Newton method. Newton method, what is the drawback? It takes a bit time. To overcome that, we are moving with another method, Gauss Newton method. Okay. So in Gauss Newton method also, what we have observed? We got an expression for the new weight. W bar of n plus 1 is equal to Wn. See, if we compare all the three, what is the common thing that we have obtained in all the three approaches? In all the three approaches, we have derived a expression for the final weight. Here also, steepest descent, the final weight W bar of n plus 1 is equal to W bar of n minus eta G bar of n. Eta is the learning rate parameter. Next, Newton method. There also W bar of n plus 1 is equal to W bar of n minus H inverse n G bar of n. What is H inverse? Hessian matrix. Next, Newton method is a bit time taking consuming process. To overcome that, we are moving with the Gauss Newton method. In Gauss Newton method, what we have observed? In Gauss Newton method, the thing is that we have observed, we have carried out a Jacobian matrix. So the final expression is nothing but W bar of n plus 1 is equal to W bar of n minus J transpose of n, J bar of n plus delta I. See, solving this only I am getting this. We are not writing any new things here. Okay. So again, we got an expression. We have made a derivation with respect to this, with respect to delta W bar, and we got an expression in terms of the new weight. Okay. So these are the things. So have a look up to here. Unit 3 very important. If you are having still any doubt, we can discuss.